Chemistry 1007 students, hello, welcome. Again, another video here. Going through chapter 9, we just covered Vesper and molecular geometry, but now we're going into, um, uh, should I say, bonds between atoms, and we will start with valence bond theory. Valence bond theory can help us sometimes indirectly figure out what the bonding pattern is for a particular molecule. Here are some very simple small molecules, and let me turn on the laser. We see two hydrogen coming together, and we remember from our electron configuration of 1s1. 1s1 defines each hydrogen, so you can imagine these two spherically shaped atomic orbitals can come together to form a molecule such as H2 gas. And Vesper is very helpful, as we know, to get to the molecular geometry. We know it's important, but we're going to take it a step further, and valence bond theory helps us to do that. We can look at, for example, a chlorine atom and a hydrogen atom. And if we think about chlorine and what we know about the electron configuration of chlorine, it's 3s2, 3p5 with respect to the valence electrons. And remember, it's just the valence electrons responsible for the bonding. So that's really the easiest way for us to understand this. We know that chlorine is short one electron, and how could it get an electron? By coming into a bond with hydrogen. Hydrogen would provide that electron that it could share and meet its octet rule and basically lower the energy by chlorine bonding with hydrogen. So that is how we can explain this. We know that chlorine has a 3p orbital, and that has an available slot for an electron, and hydrogen would only have one electron, and it can share that electron with chlorine and help chlorine meet its octet rule. So we can look at it in that these two orbitals from each atom are coming together to form a overlap of orbitals, so to speak. We're not quite to hybridization yet. We're going to get there, but we're just learning really about valence bond theory at this time. And then we're going to get into hybridization, and then we're going to go to molecular orbital theory, not in this video, but later on. And here we have two of the same atoms coming together. This is, as you see it, chlorine, diatomic chlorine. And you can imagine each chlorine is shy an electron. So if you can bring two of these p orbitals together from different chlorine atoms, you can provide an overlap here where they can share electrons and meet. They can meet the octet rule by the sharing of electrons and borrowing electrons from an electron from one another and sharing that electron, and therefore diatomic chlorine is very stable. Remember, each chlorine molecule has, each chlorine atom, not molecule, each chlorine atom has 7 valence electrons. When they come together to form a molecule, they can actually share an electron. So one electron from chlorine and the second chlorine has one electron that can be shared in a p orbital, and they can shared wise, they can have the ability to meet the octet rule and lower their energy. And when I say lower the energy, what do I mean? From a single chloride atom to a chloride molecule is to lower the energy. If I were to try to draw this in some way, just to kind of help you understand, if we had a chlorine here, and remember, this is not chloride, it's chlorine, they would be at this higher energy, just thinking that energy goes up as we go upward in the y direction. Chlorine coming together goes to a lower energy, and we'll kind of see that more evident when we look at molecular orbital theory, but it's also somewhat applicable to this overlap idea of orbitals from different atoms. But be careful Vesper is different than valence bond theory, which is what we're looking at now. And overlap, that's part of this valence bond theory. But when we get into hybridization in molecular orbitals, it's a little bit different. We can use Vesper by looking at the electron domain geometry. We can we can use the electron domain geometry to also sometimes help us understand these bonding, the how 1s and 3p come together. Valence bond theory, there's a reason for this overlap, and this overlap is going to help us reduce energy. And we know that like charges, positive and positive charges, repulse. We know that electron charges repulse. We also know that electrons can pair up, and we also know that the protons in the nucleus attract the electrons that are in the farthest region of each atom. And there can be an attraction for the nucleus of the atom's electrons and the atom it's in a bond with. Those electrons from the other atom can also, or excuse me, those protons from that other atom can attract the electrons from the atom in a relationship. If we in a bonding relationship, if we think about just a diatomic molecule. So there's lots of things going on. If we try to push two atoms too close together, the energy goes way up. The energy goes way up. Okay. And this x-axis, that we always should look at what the graph says. That's half the battle, is people looking at the graph and determining what it means. This horizontal is the x-axis, and this y-axis is energy. So as the distance increases as we go left to right, but if we go right to left, the distance starts to shrink between the two atoms, but at some point the energy goes way up. And if we start to increase the distance between two atoms, at some point we come to a minimum that's perfect. And then as we further increase the distance, we do start to raise the potential energy because the atoms are being pulled apart, and the atoms have to have a good reason to come together in the first place. And that's to lower energy by overlap of the orbitals, according to this theory. Now, there's other theories in bonding. Valence bond theory and this overlap is just one way to look at it. Here we see nucleus repulsion increasingly important if we reduce the distance between the atoms if we're going in the direction towards the left. But if we're increasing the distance, eventually we come to this maximum in energy that just kind of tapers off because now the atoms are independent. They're no longer overlaps, and there's no longer any attraction to one another. The potential energy decreases with increasing orbital overlap, and that's going in this direction, right? So with increasing overlap, we are reducing the energy till we hit some minimum. And that explains why these bonds form. They want to reduce their energy because everything tends to lower energy. Hybrid orbitals are they're mixing of these valence bond orbitals, these atomic orbitals we've already talked about, like S and P and D and F. We're mainly going to be concerned about S and P. We're not going to go into the D and F too in depth here at all. S and P in these hybrid orbitals that overlap with each other. We're mixing the atomic orbitals. We're creating new orbitals now, and we're lowering the energy. And now we're forming hybridized orbitals, which are a bit different than the shape of the atomic orbitals. So when two orbitals mix, they'll create, again, two orbitals. When three orbitals mix, they'll create three orbitals, and so on, and so on, and so on. So let's think about the electron configuration to help us understand what happens. So beryllium tends to bond with usually two other atoms, often beryllium H2, and there's some other, like maybe beryllium fluoride with two fluorides. But why is that? And what happens anyhow? Well, some of these we got to memorize, and then once we memorize it, we can think about the explanation, or we can think about the explanation and then memorize it. Beryllium has a electron configuration of 1s2, 2s2, so it only has 4 electrons. And they're telling us this is going to be an sp hybridization. How so? Well, let's just look at the electron configuration and then think about the orbitals those electrons are in. We have 1s2, 2s2, and 2p is unoccupied, but it is theoretically there. It is there. We can find out, not just theoretically, we could excite electrons and find out that they can be elevated to 2p. So we have some idea that this certainly exists. So what we can do with beryllium is we can take, we know that beryllium, if we just used our Vesper, we might sort of come up with this. If we just use Vesper and Lewis structures, we might come up with this. But it doesn't meet the octet rule. So it's a little bit different. It's not going to have 8 electrons around it. Beryllium's kind of got a small set of orbitals, only a few protons and neutrons. And so we can spread out the 2s and the 2p. We can elevate one of these electrons, which isn't too big of a stretch because the energy level is 2 and 2. So the energy is very close. We can make these degenerate, making 2p and 2s basically the same energy, which isn't difficult because they're so close in energy level. They have the same quantum number, primary quantum, the first quantum number. And so we hybridize this into sp, okay, which is usually, sp is usually indicative of linear. Where will you see sp designation very commonly is if you go into organic chemistry and you get these triple bonds, and I'm going to just do acetylene, which is linear like beryllium, by the way, but it forms different bonds to get there. This carbon here is sp as well, which typically is linear. Okay. What happens with this beryllium anyhow? Let's take the let's just think about the atom beryllium, not even in a bond yet. We take one s orbital and one p orbital, which belongs to that atom, and we hybridize the atomic orbital. Now we're doing something a little bit different. We're not just talking about two atoms coming together and forming an overlap. We're talking about hybridization within that single atom. And so s orbitals and p orbitals, and this is hybridization, not overlap. So we're kind of now in a different world. And sp hybridizes, and we form these large size and low size balloons, like a bow tie that was wrongfully tied, like a bow tie that was wrongfully produced. One side is way bigger than the other. And then they like to show superimposing these that it sort of kind of looks like the p orbital, but it's not exactly the p orbital because it has this s orbital feature. And it's actually, if we were to look, do math and look at it mathematically, would find out that this looks like these oddly shaped bow ties. Now, mixing the s and p orbitals will yield two degenerate orbitals, as we saw on the previous slide. The sp hybrid orbitals each have two lobes like the p orbital. One of the lobes is larger and one of them is more rounded. Now, do I expect you to draw this on a test? No, but kind of understand they're coming together and their shapes are malforming into a agglomeration of the two atomic orbitals into one, which is sp. This is sp, right? We created sp from s and p. Why is this even happening? It's happening because the atoms are becoming part of a molecule, and the theory is that the atomic orbitals are changing their shape to accommodate this new molecule that is being made. So in the process, hybridization is occurring. Once it's formed, but they're trying to get at how we get there. So we could take beryllium F2. So if we had BeF2, and we could, this is going to be this again is going to be sp. And so these orbitals, well, it's not going to be s if we don't have hydrogen in this case. So fluorine would just have 2p and 2p, and that can come together with beryllium. And beryllium is kind of different. It doesn't really meet the octet rule, does it? It can have 4 or even 6 electrons, and here you see that it does. It only has 4 electrons being shared between the fluorine and the other fluorine. There's a total of 4 electrons. So these orbitals become degenerate, meaning that they are of the same energy level. And the energy level has to drop for fluorine and beryllium to come together. In that very process, the energy must have went down, because if it didn't, beryllium would be better off by itself. There has to be a reason for beryllium and 2 fluoride atoms to come together. Basically, this hybridization, this overlap, we have degenerate orbitals. That means they're the same energy. This is a linear molecule. Again, this is going to be like sp again. What they're showing here is the 2p orbitals coming together with the sp. This is sp. And how is this hybridizing with fluorine? It's combining the sp orbitals of beryllium are combining with the p orbitals of fluorine. Okay, this story is kind of incomplete, and so we'll look at some other things here. We have a linear geometry, which is sp. Remember, I showed you acetylene, carbon and hydrogen, carbon-carbon triple bond, and a hydrogen forms sp as well. Now we look at boron, which is anything but boring. There is so much boron chemistry. You could teach an entire class on it, a 500-page book easily. So it's not quite as important to us humans as carbon, but it's still very, very important. And we can look at the electron configuration. We know that it has 5 protons, therefore 5 electrons as a neutral atom. And so it's 1s2, 2s2, 2p1. And so we can basically hybridize the p orbital, and there's another one that's unfilled. Remember, there's actually 3 suborbitals. There's p orbital that is occupied with 1 electron, and there's 2 empty ones over here. And so what can happen is one of these electrons can really kind of jump into here, and we can kind of like just have 3 orbitals of all the same energy. So we end up with a s, that's one of the orbitals, and then 2 p orbitals, and we end up with a hybridization of those atomic orbitals to produce this kind of triangular trigonal planar looking atomic orbital set. And this happens in the process of boron binding with another atom to become a molecule. So this is its hybridization pattern, 2 p orbitals and an s orbital, kind of like what we saw with sp, but now we have 3 of these lobes instead of just 2. And so this is sp2. If we were to look at carbon that does this, we have we could have something like this here and this here. And this carbon would be just like boron, in most, not completely like boron, but it would be called sp2. The same with a double bond with a hydrocarbon. We can have hydrogen and hydrogen, and this would be sp2 as well. Just the same kind of designation, which we use in organic chemistry all the time. So this is kind of important. Now, the most popular hybridization state between these atomic orbitals that are able to bond with other atoms, the hybridization of sp3 at the carbon. And this could be methane. It's not just methane that does this. Water, the oxygen has a sp3 hybridization in water as well. So sp3 is 3p orbitals coming together. We can see carbon's electron configuration of 1s2, 2s2, 2p2. What can happen is we can elevate these electrons, take 1 from the s. We have 3 p orbitals, right? So we can move one of these electrons over here. We could pull 1 from the s and we can create this. We'd have actually four orbitals that only have one electron in it, right? Because we have four total electrons in carbon. If we add two more p orbitals, we have room to spread out all four of the electrons, and we form an sp3 hybridized model. And so we have all these three p orbitals and the s orbital coming together and forming kind of similar like what we saw with sp and sp2, but now it's sp3 and we got an extra lobe. So now we're tetrahedral, and that's sp3. Very common. All carbons typically, if they're saturated, if they're saturated hydrocarbons, they're sp3. They'll always have four bonds to the carbon, and this is, bear with me, and this is sp3, which is also what methane would be. Water is also sp3 because of the lone pairs of electrons. We have, if we were to look at water and we were to ask someone uh, what is the hybridized or atomic orbital for oxygen when it's in when it's bonded with two other atoms, such as hydrogen, that would be, we'd find out that's sp3 as well. And that it's also tetrahedral with respect to the electron domain geometry, right? It's bent if we looked at the molecular domain geometry, but if we look at the electron domain geometry, which is what we can always do with this this sp2, and this sp3, we can look at the electron domain geometry for those with 2, 3, and 4 bonding atoms and come up with almost the same thing. So you can pull electron domain geometry into these ideas of sp, sp2, and sp3 and come up with some right answers. Water, again, as I pointed out, it has an sp3 orbital with respect to what? With respect to the oxygen. And that sp3 orbital can end up bonding with the s orbital of hydrogen. So the s orbital of hydrogen can bond with the sp3 orbitals of oxygen, just like it does with carbon and hydrogen. And this ends up being usually the bond angles for like methane, sp3 is 109.5. But if we're talking about water, because of these lone pairs, we're going to have just a little bit smaller bond angle at 104.9 because of the non-bonding electron pairs have strong repelling powers and compress the bond angles and shrink the bond angles a bit. Okay, so this sp3 is very, very common in organic chemistry. So hybrid orbital summary, you draw the Lewis structure of the molecule, use VSEPR, make sure you understand the electron domain geometry, and then you can start thinking about how the atoms come together to form this molecule, and you can label them sp, sp2, sp3. And here's a summary of what we just talked about and some examples. sp atomic orbital sets for the central atom, which is beryllium, comes together to form sp. And so you get two sp orbitals that can bond with fluorine, or with mercury, can bond with chlorine. We could have an s and a p orbital. We have three sps. They come together to form a trigonal planar at that central atom. So boron can form this trigonal planar structure, and so can sulfur in this sulfur trioxide molecule. Now remember, this also works for double bonds in carbon. So carbon double bond to another carbon also gives sp2. We can have SPPP. This is for methane or for water, and the atomic orbital of carbon or oxygen forms an sp3 hybridized model, so it can bind with other atoms, such as with the s orbital of hydrogen, or with nitrogen bonding with the s orbital of hydrogen again. So this is very common. Typical geometry is tetrahedral. So hypervalent molecules, we'll get into that a little bit, but not too much until you get to inorganic chemistry in your junior or senior year, if you decide to take that. Valence bond model would use d orbitals to make more than 4 bonds, because d orbitals are 5 orbitals. They can hold up to 10 electrons. So and then we have other species that have really interesting 18 electron rule, where you can have multiple bonds. So these d orbitals are typically around period 3 and below. And you use this hybridization model to help with understanding this. This is not the only model to understand how atoms come together to form molecules. This is a very easy one because we can extract what we learned from Lewis structures to VSEPR to get the electron domain geometry, and then to get the molecular geometry. If we just rely on the electron domain geometry, we can figure out what that central atom is. Is it sp, sp2, or sp3? So, and with that being said, if we were to have an example, say it was PCl3, okay, and this here, as we know it, we did the electron domain geometry. We have a one lone pair of electrons, and then we have chlorine coming out here, and then we have chlorine here, and so we get this trigonal pyramidal system with respect to the molecular domain geometry. But if we count the lone pair of electrons, we get a tetrahedral molecule, and tetrahedral means this has to be sp3, right? It has to be sp3 with respect to the phosphorus. And then chlorine has p orbitals that it can donate to the central atom. So that is it for now. I'll be back soon with more materials from Chapter 9. Thank you, Gen Chem 1 students. I'll talk to you later.